All right, welcome back. We're going to talk about logarithmic differentiation. Prerequisite for this video would be the rules of differentiation, as well as implicit differentiation, and some knowledge about the rules for logarithms. So remind yourself about those rules as they do apply to the questions that we're going to see. There's two types of logarithmic differentiation approaches that can be used depending on the context. So for example, the first type would be that you are going to leverage those logarithm rules. For example, here I have log base b, but it could be the natural logarithm for simplicity. Any base wouldn't matter, but the natural logarithm is actually the safest way to do it, the cheapest way. The second type is that you have a base and an exponent that both possess variables. So in other words, for example, x to the x or something more complex like that, that would be another situation with logarithmic differentiation being useful. Here's some examples that we'll cover in this video, 4 to be specific. The two on the left involve several rules of differentiation, including product, power, quotient, and chain rule. And on the right, we have a base and an exponent that both possess variables. The strategy that will be used for logarithmic differentiation includes taking the natural logarithm of both sides and then using implicit differentiation. So for example, if I take the derivative of ln y with respect to x, we would have the reciprocal of y, and then the chain rule would take into effect here because y is implicitly in terms of x defined, and there you have that. And then ultimately you want to isolate for dy dx to complete the problem. So here we have a product of two functions that are very complex. We have a power of a function multiplied by a power of a function. Step one is to take the natural logarithm of both sides. So if you do that, you can see that we can apply the rules for logarithms. We can split that up as follows. And then you see the exponents 5 and 6. We can use the power rule for logarithms and bring those exponents down. So I'm trying to show the rule on the right there as we're going through that. Now, the idea is that the line of writing here, this equation is much easier to differentiate than the original because you have separate terms that involve logarithms. On the left, using the strategy I mentioned, we would do the pattern of 1 over y dy dx. And on the right, let's differentiate term by term. So let's put the 5 down as it is a constant. The derivative of ln of 2x plus 1, we take the reciprocal, and then multiply by the chain rule. So we multiply by the derivative of 2x plus 1, which is 2. And then you can put that on the numerator. Hopefully I'm not talking too fast on this video. There's a lot of algebra, so just want to be a little bit of a motor mouth here. Anyway, let's do the second term. We can take the 6 and just put it down as a constant. And then the derivative of 4x minus 7 within the logarithm. So we would have the reciprocal, and then the derivative of 4x minus 7 is 4 on top. We can multiply the numerator 2 by 5 and the numerator is 4 by 6 to get a simpler expression there on the right. And the only thing now we have to do is to get that y on the other side so we can isolate for dy dx. This will always be the case. So what you're going to do is just move the y over by multiplying both sides by y, and then replacing y with the original function. And there it is. That's the process. And hopefully it looks scary, but believe me, if you apply the power rule and the product rule, for this one, it's okay, but arguably this is kind of a safer bet in terms of what you can do and the mistakes that you can avoid. The other approach involves a bit of factoring to simplify, which often is annoying for students. And you might be like, well, I can do this one. Well, let me motivate you by giving you one that's worse. Let's see here what happens when we use the natural logarithm to split this up. So I wrote the root as a power of 1/2, just as a starter. And let's take the natural logarithm of both sides. If you're worried, this is the longest example you'll see in the video, so hopefully you're still going well. And of course, you can pause each step because that's a lot of writing here. Anyway, let's split those up using the rules for logarithms. So we have the logarithm of a product and the logarithm of a quotient. So we can add the two numerator terms separately and the denominator will be subtracted. So there's the two rules in action for those three terms. Now, we can use the power rule for the logarithm to bring those exponents 7, 8, and 1/2 to the front. And here we go with that. So that exponent, each exponent will go to the front. And look, it's basically like the previous question, except there's 3 terms instead of 2. So 50% more writing from this point on. Let's do the derivative on the left side, which is the 1 over y dy dx pattern. And then we'll do term by term here. 7, we just copy that constant. The derivative of the first logarithm is the reciprocal multiplied by this chain rule inside, which is 22x. Repeat that for the remaining terms. So write that 8, reciprocal, and then the chain rule with a 5, and then copy the negative a half, reciprocal, and the chain rule would be a 12x. We can clean up those numerators with the outside constants. It just works a little bit nicer there. So 7 times 22, 8 times 5, and half times 12, of course, with the appropriate x's for each term as they are present. So there you go. Now it's a matter of bringing that y over to the other side through multiplication or whatever you want to call it. Call it cross multiply or sort of cross multiplying. In any case, replace y with the original function in terms of x, and then you have the ultimate answer. Now, this one here, like I said, 50% more writing in terms of the derivatives, but a lot less writing than if you try to do this using the other rules. It's fine to do it both ways. It'd be nice to do it the other way and to compare the two because they would eventually equate to each other with a little bit of algebra to help. So that's the first type of a problem that we're doing, which is when you have a complex function involving several terms in the numerator and possibly in the denominator, several brackets where you want to split them up using the rules of logarithms. So dividing and conquering, if you like. The second type of problem involving logarithmic differentiation is when the function has a base and an exponent that both possess a variable. In this case, this is the simplest possible or reference type function that we can have. So step one's still the same. Let's take the natural logarithm of both sides. The trade-off is this. I don't know how to differentiate x to the x otherwise because I know how to differentiate, for example, x squared, but not an x to, and 3 to the x, for example, but I don't know how to do x to the x. That's kind of weird based on if you were progressing through the videos that we've shown so far. So in this case, though, we can use the power rule for logarithms to bring that exponent to the front. And now we have a trade-off. An original function that potentially you don't know how to do, you've replaced it with a function that looks like a product rule and implicit differentiation on the left-hand side. So let's do that. The pattern for the left is as the previous examples. That's carbon copy every single time. And now on the right, we have a product rule. So if you forget the product rule, that's probably the third video in this series, I believe. So we do the derivative of the first term, the first part, and then leave ln x alone, leave the x alone, and the derivative of ln x is 1 over x. The second term, their x times 1 over x, simplifies to a 1. Now we're in the clear. You see a lot less writing, but a much more interesting question in the sense that it's weirder than the previous one. The other one was just a lot of brute force. Anyway, bring that y over through multiplication and then replace it with the original function, and you're good to go. So let's move on to a more general situation. We have here a base that's trigonometric and an exponent that's a power function. Now, let's apply the pattern as before. By taking the natural logarithm of both sides, we can bring that exponent down using the power rule. And now you have replaced the original function, which was a more high level, I guess, in terms of it exists a variable in the base and the exponent. You traded it off for an implicit function and a product rule and a chain rule. But I'll take the latter all day. Anyway, left-hand side is the pattern as before. And on the right-hand side, we have a product rule, including a chain rule within the logarithm. So the derivative of x cubed, leave the second one alone, leave the x cubed alone, and the derivative of ln of sine of x is going to be the reciprocal, 1 over sine x, multiplied by the derivative of sine via the chain rule, which is cos. You can take that last bracket and write it as cotan if you like. You don't have to do this step here. I did it because it just looks a little bit, I don't know, streamlined, I guess. Anyway, clean it up a little bit more. You could factor out x squared from both of these terms. I didn't bother at this point, but you could. Anyway, bring the y over, replace it with the original function, and there you have it, an answer to a more difficult question. For those of you studying in university, maybe first year, you probably will see this kind of question on a calculus exam. Maybe it's if your course runs 3 tests, it'd probably be the first test. If it was a 2-test exam, probably the midterm, kind of like a first semester, first year. Sometimes you might see this in high school, but I don't know where you're studying. In the Ontario curriculum here in Canada, this has been essentially kind of phased out of the core curriculum, although it did used to exist more prominent in terms of when I was in high school. So anyway, which was a while ago. I hope you enjoyed this, and I'll just keep on grinding out some more videos. Thank you.